So let's continue. And after having seen the freeze-out of dark matter particles, we continue. The story of the universe proceeds. And we're going to encounter various processes, as I already mentioned. But first, let's place the stage, no? For early times, to see what do we expect to have there. So here we are talking about temperatures, when I talk about early times, that are of the order of 0.53 mega electron volt. So that's the range of temperature that we are talking about. We have relativistic and non-relativistic species. Not all, we are talking about relativistic species are ruling at the beginning of the universe, but this doesn't mean that they are all relativistic. Okay? Photons are relativistic, and light particles are relativistic, neutrinos, for example. The others that have larger masses for the same temperature, they are not relativistic. And again, the distinction comes clear when you look at the distinction between mc squared divided kT, right? If this is fixed by the ruling thermal species, photons, then according to the mass, this can be larger or smaller than kT. So the larger is the mass, the more likely is the particle to be non-relativistic. Okay? So for the same amount of T, larger particle can be non-relativistic. For the same T, smaller mass are more likely to be relativistic because of this ratio. All right. So let's give a look at the relativistic ones. The relativistic ones are going to be the photons for an obvious reason. They're just relativistic always, at every time, because they have zero mass. Neutrinos that have a mass estimate of this order, let's say, so they are very light. This comes from constraints from cosmology. And from the oscillations of the solar neutrinos, okay? Cosmological constraints are tighter than the one coming from the oscillations of the solar neutrinos. And then we have the electrons. So you see, the neutrinos up to this temperature, where we have equality, where that ratio is equal to 1, before they are relativistic, after this temperature, they are non-relativistic. Then we have other particles, non-relativistic, and we have, for example, the muons, mu, 105 mega electron volts. We have the protons, 940 mega electron volts. That's similar to the mass of the neutrons. Neutrons are a bit smaller. Then we have the top quarks and so on, W, the Z, and so on and so forth. The Ws, the Z, and so on, all the other particles. I mean, we're not interested in those within this context. All right? So you see, we have relativistic and non-relativistic according to the temperature. That's the key concept that I want to give you. Then we have a universe which is filled up by photons. So the dominant component is given by the relativistic species. So this guy here are the ruling components for the expansion. That's why we speak about the relativistic particles are ruling the universe at this time, because their energy density is much larger with respect to the other ones. Okay? The omega whatever of the others. Okay? And this sets the expansion of the universe. It doesn't mean that everything is relativistic. They're just ruling in terms of energy density. Then we have the temperature data scaling. With respect to the density, so for relativistic species, so we have seen then when we did quantum gases, 30G star kBT over h bar c. This is to the power of 4, and this is to the power of 3. That's for our relativistic plasma, okay? And again, just to give you a number, the ratio between number of baryons and number of radiations is of the order of 10 to the minus 8. Okay, so baryon are rare stuff at that epoch. All right. Then you see we have our G factor that accounts for the internal degrees of freedom for the available particles. And the relativistic one that we are considering are going to be our photons. We have electrons, we have the positrons, then we have the neutrinos. Remember that there are of three flavors. There are the electronic one, the mu one, and the tau neutrinos. If we count their internal degrees of freedoms, then our G star is 10.75. This goes here. Here you have the spin that sum up together. The sum is 10.75. All right. And as we said, at the beginning, we have equilibrium. So all the reactions have a reaction rate much larger than the expansion rate at the time. And the kind of reactions that we are going to deal with, there are many. Let me give you some. So we have, for example, scattering between neutrinos. This could be electron-electron, could be muon tau, muon electron, and so on and so forth. So we have scattering, and we have therefore the same particles on the other side. So this tells you that neutrinos are interacting one with each other effectively, and they are therefore in equilibrium one with each other. Then we might have interactions of this sort, like neutrino plus electron, and we are getting neutrino plus electron, another scattering process. What is going to tell you? That the neutrinos are in thermal equilibrium with the electrons. And then we have interactions, for example, with the protons. We are going to have, for example, neutrino of the electron type that turns into a proton and an electron. So you see the neutrino are in contact with the protons. Again, always weak interactions we are talking about for this sort of processes involving neutrinos. Or again, we are going to have annihilation of electrons that gives you neutrinos, an antineutrino, or, and then I can go forever, for example, annihilation that gives you photons. So you see, everybody is talking with everybody. Maybe the neutrino are not interacting with the photons, but they do through the electrons, because they are in thermal equilibrium with the electrons that in thermal equilibrium with the photons. So we have a global equilibrium of all those species. All right? Okay. Before, when I was speaking about the L particles before, and we always kept them in equilibrium, that's because they were in equilibrium. I showed you one reaction, but there are all these gazillions of reactions that are taking place. So in equilibrium. Okay. Where the temperature is set by the photons. That's because they are ruling species in terms of number. They set the entropy of the universe and the temperature of the universe. So they are the reservoir, the thermal reservoir of our universe. All right. Let's now that we have our setup, that's the universe we are talking about, we give a look at the neutrino decoupling. So, what happens? Neutrinos are coupled through the weak interactions with electrons. So we have, for example, the annihilation between neutrino, electrons, neutrino, and antineutrino, and the electrons. And we have, for example, our electron neutrino plus an electron that give us another neutrino and again an electron. So we can have this annihilation process, or we can have a scattering process, and keeps the two guys in equilibrium. And the reaction, let me stress it now, depends on the velocity at which the reaction is taking place. Yes, depends on the temperature because there is the velocity dependence, but it depends also on the cross-section that in this case is going to be the weak given by the weak force. So we have our Fermi constant, and the cross-section scales with the temperature. I don't go into this particle physics stuff. I just give you a few elements so that you can, if you know it, you know it. Otherwise, you can look into it. Fermi constant. So that's the cross-section, and that's for the weak interaction. All right. Yeah, just to complete the picture. So we have our weak interaction rate, which is given by the number of electrons. We have the weak force cross-section, and then it's the velocity dependency. All right. Good. Then let me not write it again. We have rho r that is for our thermal species. I wrote it there for our relativistic species. Then we have our, so that's a function of the temperature. And then we have the Hubble function, 8 pi g over 3 rho r, that again, through this expression, is a function of the temperature. We want to know when the freeze out is occurring. Well, it's easy. That's freeze out. That's very, very simple consideration here again. We should use the Boltzmann equation for having the right number, but we can set that I cannot do it because we have only one numerical, one numerical evaluation of it. And this occurs roughly in 1 mega electron volt. Right, we have two neutrinos. Look at the mass of the neutrinos. That's half of it. Okay, that's when you get the freeze out. To do it precisely, we don't go very, very, very far from that because we get 0.8 mega electron volt. Right? When this happens, we have our annihilations. So this is just another channel for the equilibrium. This annihilation is going to stop. And what we are left is with these guys. We have neutrinos that are not interacting anymore with the other species. This is our neutrino background. Relics. Cosmic neutrino background. Now you can, yeah?
Why is this direction of the process continuing? Because the electrons and positons are the particles with stress mass.
No, you cannot anymore at a certain point. If you follow the Boltzmann equation, you have at the end that term there that is popping up and is killing the reaction.
Yeah,
So the process in this direction is going to be forbidden. Exactly as we did, exactly what happens before. So the thing is that we have always a reaction rate and an expansion function as a function of temperature. And since the reaction rate is for this interaction is steeper than the Hubble factor, we are going to have freeze out.
yeah, I get this, but like the electron, positron, regardless of the energy, they should always be able to form a neutrino pair because neutrino is more or less mass.
Yeah, it have a very, very small mass.
But neutrinos
It just happens to be at this energy level. Just by following just by doing that. Okay? Then if you have the annihilation of electrons and the production of the photons, that this is strictly related to the mass of the electrons. Because you need to have enough mass of the electrons to produce a pair of photons with a certain energy. I'm arriving at that. This is just done. This is just the freeze out is all given by the Boltzmann equation. And the simple criteria, just to have an order of magnitude estimates, is coming from the freeze out condition. Reaction rate and expansion rate. Okay? And by doing the number, this is just what comes out. You are around 0.8 mega electron volt.
But what you said right now was also like you can always annihilate electron and positron to a photon. You cannot. That's what you said is also the other way around. The photons need to have a certain amount of energy
To create the electrons. Yes,
photons.
correct.
And here it's exactly the same. The neutrinos need a certain amount of energy.
Yes.
The energy to electron and positron. So therefore, at a certain energy, exactly the other way around is forbidden.
Yes.
Yeah, but you wrote it the other way around on the blackboard.
What did I write?
I think that the arrow on the bottom equation has to be pointing to the left.
Here. Yeah, okay. Yeah, okay. So, anyway, yes. So the interaction is stopped. Okay, that's the point. Yes, the arrow, yes. Okay, thanks. Good. All right. Okay. Then we are going to have a relic. So you might think, okay, nice. We have a relic contribution. This might be dark matter. Why not? They have a mass. Neutrinos do have a mass. And the interaction rate is extremely, extremely low. And we might not see them in abundance. The reactions are not taking place in abundance in the universe because densities are very low, and they're unobservable. That's fine. Okay? But it cannot be. Why? Because you have this expression, rho r, that is set in the distribution. You can compute omega of your neutrino. Now let's call it with the nu, which is just, again, definition of rho of your neutrino with respect to the rho of the critical density. Right? This one is coming from this relationship. We can compute what is the number of neutrinos that we expect. This one, then we have the mass of the neutrino, that, as we said, is very small. I wrote it somewhere, don't remember, here. And if you sum up all the masses of your neutrinos, you do not arrive at the right number. Okay, you can compute n nu. So if you sum up all the neutrinos and you have your total mass of neutrinos, then you can compute a density. You divide by the critical density, and it's not enough because the mass of neutrino is very small. You arrive at an omega neutrino, which is of the order of 0.01. Whereas what we need is an omega matter equal, of the order of 0.3, orders of magnitude too low. So neutrinos cannot be your dark matter candidates. Okay? That's why one points at non-standard model particles. All right. Then what happens? Something cute. Is electron and positron annihilation. Also, that reaction stops. That's one of the reactions that I wrote up there. So we have a positron and electrons that can annihilate, forming 2 photons. And you have equilibrium up until a certain threshold of temperatures. Because remember that the temperature of the universe is given by the photons. They are the ruling species from this point of view. And these guys have a certain distribution, right? The Bose-Einstein distribution, which has a cutoff. And that distribution depends on the temperature of your photons. Remember the Planck spectrum, it has a temperature dependency, right? High temperatures, photons with higher energy, low temperature, photons with lower energy. And to allow this process, on this side, you need at least an amount of energy necessary for the pair production of your electron and positron. Okay, mc squared to the power of 2. Mc squared times 2. Mc squared, mc squared. That's the energy that you need on this side to go in this direction. But the temperature is going down. Therefore, if you take your distribution, here you have the spectrum for your radiation field. Let's call it the power of your, as a function of the frequency. The Planck spectrum looks like that for a certain temperature. If we decrease the temperature, what happens is that the bell is shifting in this direction. These high energy photons are not there anymore. And whenever you hit the threshold to mass of the electrons, then you don't have anymore the production in this direction. The reaction stops. Okay? In this direction. What happens, therefore, is that your reaction can only proceed in this direction. You have the production of photons, because here you have an energy content, and you can produce photons with an energy that is given by the kinetic energy of these guys plus their mass content. You know, you have just energy momentum conservation has to be respected. And on this side, you can go without particular constraints. Okay? Quindi this one continues. What happens? Imagine the photons that are not participating to this interaction. You have the temperature of those photons, and it's going down. Now let's take one of these photons, well, these pairs of photons that are produced. Okay? The energy is set not by the expansion of the universe or whatever, but by this process, which carry at least this amount of energy. Therefore, you have a production or population of photons that have an energy. Now, it's all the order of m2e. I mean, it has a distribution, but let's keep it simple, which is fixed. Therefore, and with that, you can relate it to a temperature. Therefore, let's better say to an energy injection of photons that have an energy larger than this one, whereas the energy of these photons is going down, down, and down. Okay? Overall, you have a population of these guys and a population of these guys. You have a reheating phase. You have injection of energy into the radiation field. Okay? What's the catch here? If that interaction would have not stopped, then you have equilibrium between the two species, meaning they have the same temperature. The electron will give energy to the photons, and they will follow each other. But they're not talking with each other anymore thermally. They are decoupled. Therefore, you have this radiation field of the photons that are there that is taking its energy. Neutrinos are not anymore in equilibrium. Contact with the photons up there through the electrons, via electrons. Okay? If they have no contact, you have initially, you start with neutrinos that have the same temperature of the electrons when there is the reaction. Reaction on. When there is not any more contact, the two can evolve independently. Okay? But we have that T goes as a to the power of -1 for the neutrinos, and T goes as a to the power of -1 for the photons. They don't talk one with each other anymore, so they have the same temperature. They don't talk anymore one with each other, and then thermally they evolve with the same temperature evolution, right? Therefore, they keep the same temperature up to this point. When this happens, we have the electron-positron annihilation, and we have a production of, and we have an injection of energy in the photon fields. The temperature of the radiation goes up. And we are going to have a temperature for the neutrino, for the radiation, let's do it like this, which is larger than the temperature of the neutrinos. Okay? Reheating process. Yeah?
So here you say on the left that the production of the photons continues, but on the top right, in the case of the neutrinos, you said that the reaction stops in both directions. So why doesn't the neutrino production still go on?
Because you can, this guy can always annihilate. There is nothing that forbids them not to annihilate.
Yeah, but then nothing stops them up there as well? Or is there any reason they don't annihilate up there?
That's because they don't have anymore the chance to meet because of H, so to say.
So the argument is that the universe now is so big, they don't meet anymore.
I mean, it's always matter, I mean, there it's what is ruling is so here is not happening a freeze out like that one. That's a thermal freeze out in which the reaction rate is lower with respect to the one of the universe expansion. Okay? It stops. It doesn't go in one direction, it doesn't go in another direction. It's completely off. Here we have an equilibrium. This reaction is possible because of that. And then at a certain point, these guys that have a certain temperature do not have the sufficient energy to go in this direction. So they could meet, okay? But they cannot. Because here they don't have enough energy to produce this amount of energy. That's 2m, this 2m c squared for the electron. And here you would have h nu for the photon 1 plus h nu for the photon 2. At this point, you have that. This can enter 4, the reaction stops. Okay? All right. So it's an energy constraint that is playing the role. Okay, all right. So we have an injection of energy coming from the photon to the radiation field. And you understand that there is an increase in temperature of the photon relative to the temperature of the neutrinos that now are not anymore coupled. And therefore, they have an independent, their temperature can evolve independently. Cute thing, we can count, we can compute very easily what is the difference in temperature. And this comes from thermodynamics, because in the universe here we are dealing with adiabatic expansion. We've seen that there is entropy conservation. Therefore, we can make the computation of the entropy before the reaction and after the reaction. I mean, of the two sides of the equation. So what do we have? We have the entropy of the positons plus the entropy of the electrons plus the entropies of the photons. That's before. Afterward, we have the entropy of the photons only. Annihilation stops. We just have this term that is playing a role. Then we have, when we did the quantum gases, we computed what is the entropy for entropy density actually, the entropy density of our fermions, and that's equal 7, 8 G for fermions over G for boson, and then we have the entropy density for the bosons. That's we've done this from the quantum gases, quantum gas. All right. Where we have that G e positron is equal to G for the electron, which is equal to G of the photon, and they're both equal to 0. Therefore, if we make the ratio between SF and SB, we get 7/8. Okay? I just get the ratio here, and I plug in the number. This drops. I'm left with 7/8. Therefore, this equation is just becoming 7/8 for our electrons, for our positrons, 7/8 for our electrons, plus 1 for our photon times S gamma. So I just 7/8 S gamma, 7/8 gamma, and then S of gammas. I just group the S gamma together. And that's equal to this guy here. And that's it. Having that, I have the relationship with S of our bosons, which is G boson K 2 pi over 45 kT over h bar c to the power of 3. So you see I have the dependency with respect to the temperature. And what we obtain is 1/2 T gamma is equal to T gamma prime. And this is measured. Yes. So we have that the temperature after the reheating process is 1.5 times larger than the original one. All right. Therefore, if we are looking at the temperature of the photon 2 days, that's something measured. That's roughly 2.752 Kelvin. This is measured. That's cosmic microwave background measure. Therefore, our neutrinos are going to have a temperature of 1.95 Kelvin. And that's expected. Okay? Expected because neutrinos are interactive very poorly with matter, and we only detected neutrinos coming from supernova explosions. Those we have. We have neutrinos coming from the sun. These we have. We have neutrinos coming from decays. These we have. But the cosmic neutrino background, we do not have. Okay? So, what happens with this below the reheating? Let's get rid of here. Let's go for the decoupling. Ta, 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 ta. And that's what we have. All right. So here is the expansion function. So we are going as a function of time in this direction. That's the temperature of our fluids. At the beginning, we have equilibrium, okay? And the temperature goes as a to the power of -1. That's the straight line. That's radiation that continues like that. At the beginning, we have equilibrium, same temperature. Then we have neutrino decoupling, you see here. And the two temperatures are evolving in the same way because they have the same dependency with respect to the expansion of the universe. But they are already decoupled. When our annihilation process stops, when the annihilation stops, when this equilibrium stops, we have the reaction going in this direction only. We have injection of the photons, of the energy of the photons into the radiation field that get boosted. You see, neutrinos just continue with the temperature that they had, and it drops just because it's of the expansion of the universe. Photons get this reheating process, get a kick in the energy, and then after the reheating process is gone, they will continue again with the same temperature, parallel one with each other, but a difference that can be derived by simple consideration based on the entropy. All right? Good. So that was the second phenomenon that we encounter. So we encounter freeze out of dark matter. We use the Boltzmann equation that was specialized for the case of dark matter annihilation, as we have seen, giving us the Riccati equation. Then we continue with the processes. I described the processes, the property of the universe at the early times, equilibrium, all the reactions between the different particles such that everybody could talk one with each other, even indirectly, but they do. First phenomenon that occurs is the decoupling of neutrinos from the electrons. And since there is not anymore decoupling between neutrinos and electrons through the weak interaction, they are also decoupled from radiation, because electrons are coupled with radiation. The bridge connecting the interaction between neutrinos and electrons is broken. Therefore, the temperature of the photons and the temperature of the neutrinos can evolve independently, but at this point in the same way. The universe is expanding in the same way. They're both relativistic species, and the temperature evolution is the same. So they keep the same temperature level, up to the point in which we have this equation that breaks out, okay? The electron-positron annihilation giving photons, at a certain point, stop to proceed in this direction, cannot proceed anymore in this direction. The photons are too cold, have too low energy to produce electrons. The reaction goes only in this direction, and we have, therefore, the photons in the field that are going down in temperature, but the photons that are produced through this process have an energy which is at least of 2 mass of the electron to the power of to the c to the power of 2. Okay? Injection of energy that creates this reheating process, leading to this energy difference, temperature difference that can be constrained through simple entropy conservation considerations. Okay? With this, we stop. Thank you very much. Tomorrow we continue with the baryonic, the BBN, the Big Bang nucleosynthesis, and hopefully the coupling of the photon radiation from electrons. Thank you very much. I see you.